Okay, we are going to do a couple of more examples with Euler's theorem. The first of them, let's try to work mode 12. And if we try to compute 6 at power, let's say 2019, mode 12. Can we apply Euler's theorem to speed up this computation? Remember that Euler Theorem says that A at power Euler tangent of a number n mod n equals 1. And it only applies if greatest common divisor between A and n is 1. In this case, our n is 12, our A is 16, it's 6. The greatest common divisor between 6 and 12 is 6, it's not 1. Therefore, we cannot use Euler's theorem to speed up this computation. We also could not use Fermat theorem here because 12 is not prime. Fermat theorem applies to primes. Euler theorem doesn't require primes, but requires the base as the exponentiation to be coprime with the modulus. Okay. So there are mod 12. There are a lot of numbers for which we cannot apply Euler's theorem. Anything that has 2 and 3 inside, right? So the only kind of numbers for which we can apply Euler's theorem mod 12 will be 5, 7, and 11. Right? So let's take, let's say, 5 at power 2019, and let's compute this mod 12. To be able to compute this mod 12, we are going to first compute Euler tangent of 12, for which we decompose 12 in prime factors. It's 2 squared times 3. We apply the previous result. So it's Euler tangent of 2 squared times Euler tangent of 3, which is 2 times 2 minus 1. And here we get 3 to the power 0 times 3 minus 1. Altogether, this makes 4. So Euler's theorem tells us that 5 at power 4 is 1 mod 12. So to exploit this, we are going to say that 5 at power 2019, we are going to rewrite the exponent to be able to exploit the power 4. So we say this is equal with 2016, which is a multiple of 4 plus 3. So it's congruent further with 5 at power 4 times 504 plus 3. 5 at power 4, everything at power 504 times 5 at power 3. 5 at power 4, now we know it's congruent to 1. So this is 1 at power 504, it's 1. So we remain with 5 cubed, which will be this time 25 times 5. 25 mod 12 is 24 plus 1 is 1. So it's 5 modulo 12. Okay. So we notice that a similar trace as a computation will happen for all the other bases. Mod 12, namely mod 7 or 11, will have the same decomposition as the exponent if we try to raise the power to 2019. And the differences will be only here. Let's say 7 at power 2019 will be congruent eventually with 7 cube, exactly as before, which is 49 times 7. Now 49 mod 12 is 48 plus 1. It's again a 1. So it's 7. Mod 12. If you don't have an immediate idea how to break the exponent such that it's separated into a part that can be reduced, you are going to divide it. Let's say 2019 in our case. I divide it by 4, and that will return you 504 like here, and the remainder 3. And this will help you to jump directly from an expression like this to an expression like this one here.